In this video, we're going to talk about bases, but first, we're going to talk about linear dependence. So we say a set of vectors say v1, v2, vn is linearly dependent if you can get zero when you multiply them by constants. Let me use a constant, say C1, V1, C2, V2, Cn, Vn. If you can get that to be zero, when not all the C's are zero. So if you have a set of vectors and you can multiply them by some constants, not all zero, and get zero, then the set of vectors is linearly dependent. Now the set is linearly independent. If C1, C2, V2 plus Cn, Vn is zero only when all the C's are zero. That is when C1, C2, all the way up to Cn are all zero. If that's the only way you can get this linear combination to be zero, then they're linearly independent. Now, of course, you're always going to get zeros when you make the constants zero. But if that's the only way you can make this come out to be zero is to have all the constants zero, then it's linearly independent. On the other hand, if you can find some constants, they could be a mixture of zero and non-zero, as long as they're not all zero. If you can find some combination of constants that such that this will come out to be zero when they're not all zero, then they're linearly dependent. Now, there's sometimes it's easy to determine if a set is linearly dependent. Again, sometimes you do have to go through a lot to find the constants that make this zero. But once in a while, it could be easy. So we can note several things. If any two vectors in a set are scalar multiples of each other, then the set is linearly dependent. Because you could see, for example, if let's say, like let's say just pick these two vectors. If these are scalar multiples of each other, let's say if you can get V1 by multiplying V2 by 5, then you could make this to be 0 simply by making this 1 and this 5 and all the others are 0. So if you have any pairs that are linearly dependent, or a scalar multiple, you know automatically they're linearly dependent. And if the 0 vector is in the set, then the set is linearly dependent. Once again, you can see this from our original set. If one of these vectors was 0, then you can make all the other constants 0 and make that constant times the 0 vector, whatever you want, and this would still be 0. And of course, if you add a vector to a linearly dependent set, that's only going to make it worse, you might say. It's certainly not going to make it better, because you can, whichever vector you add, you can make that constant 0 and just make all the other constants whatever you used before to make the set 0. So if you add a vector to a linearly independent set of vectors, the new set will still be linearly dependent. Or if you take away a vector from a linearly independent set, the new set will still be linearly independent. Now we're going to talk about a basis. And so a basis . basis for vector space V is a linearly independent set of vectors which span vector space V. A basis for vector space is the linear independent set of vectors which span V. And there's several things you can see from this. The idea is the basis is kind of the sort of the ideal set, such that you can get every vector in the space by taking linear combinations of the basis vectors. Because notice this set of vectors has to span V, and it's also linearly independent. Now the fact that it spans V, again, remember the span means you can get any vector in the space by taking a linear combination of the basis. And the fact that the set is linearly independent means you really don't have any extra vectors in the set. So now notice several things. Note, if you add any vector to a basis, then that set, again, that set of basis vectors, which you've now added one to, will be linearly dependent. And you can kind of see that real easily. You know, you could actually sort of, I said this as a note, you could even call this a theorem if you wanted to. Let's say if you could sort of prove that. So proof, suppose you have a basis for a vector space V. Now add any vector, and let's call that vector, I don't know, let's call it maybe V star to the set. Now, since the basis spans the vector space, that means you could get this new vector by a linear combination of these vectors. Then there exists say C1, C2, Cn, such that and let me say one more thing, not all zero. Such that C1, C2 plus Cn, Vn will give you that V star. Because, by definition, the basis spans a space. So any vector you come up with will be a linear combination of the best basis vectors. And now just rearrange this a little bit. Let's bring this V inside to the left-hand side of the equal sign. And so now, once again, what you're going to have here, you're going to have these vectors all equal to 0, but the coefficients are not all 0. Some of these C1s we said, because some of these were not 0. And of course, this negative one in front of this V star is not 0. So therefore, the new set let's call it like this, with our V star, and if that's clear, that star is linearly dependent. So in many ways, then, as I mentioned, the basis vectors, the way the basis is defined is kind of the ideal spanning set. It spans the space, but doesn't have any extra vectors. Another thing that we can say is any linearly dependent set of vectors that span a vector space V. Let's say they span V and they're linearly dependent. This set can be reduced to a basis. And so, for example, again, let's say you have a set and let's start with a case. So let's start with a case where the set does not have the 0 vector. If it has a 0 vector, you can eliminate that to start with. And then let's say it's still linearly dependent, but again, the set spans the space. So let's say you have something like this. So you'll have something like this where the CIs are not all 0. And so what you can do is, let's say with any ones that aren't zero, let's say one of these isn't zero. And you, of course, if you don't have the zero vector in the set, then, and you still can make this zero by having some C's that are not all zero, you'll have at least two C's that are not going to be zero. That you can't just have one not zero if you don't have the zero vector in there. And then what you could do, so let's say you have some of these are not zero, and then you could rearrange these. Let's say, for example, C2 is not zero. You could rearrange this. And again, let me take out C2. Let me put in C3 plus CNVN is minus C2 V2. So let's say I bring it on the right-hand side. Then notice, like I said, this V2 is going to be a linear combination of these. So that means you can eliminate V2 because it was sort of a vector you didn't need, because you can create it by using the other vectors. And then you could keep doing that until you got all the constants to be zero to make this zero. So if you have, again, as long as they span the space, you can always reduce your linearly dependent set to a basis. And now we also have something called the dimension of a set, or excuse me, of a space. Dimension of a vector space is defined by the number of vectors in the basis. And that's supposed to be vector space. The dimension of a vector space is defined as the number of vectors in the basis. So if your basis has 5 vectors, then your dimension is 5. And again, I'll put some theorem down that we'll prove later on, is any basis, let's say all bases for a vector space will have the same number of vectors. So if you, because a vector space can have more than one basis. In fact, usually have an infinite number of different bases, but they'll all have the same number of vectors. And let me give you a simple example. Consider, say, R3. One basis would be the standard basis. You can easily show that these are linearly independent. And you can also show that you can get any vector in R3 by simply multiplying the first coordinate by this vector, the second coordinate by this one, the third by this one, and add them up. Also, another basis for R3, we could maybe do, say, something like this. Let me still keep it pretty simple. So this again would be a linearly independent set. You could check that out by noting, like, if you tried to put these two vectors, if you try to multiply these two vectors by something to get this one, there's no way you could do it because you could not create anything in the y position. So these are three vectors that are linearly independent and they span the space. So here's for R3, we have a couple of different bases. And so based on this, you could go one step further. You could say, so again, say for R3, once again, as I mentioned before, based on a definition, the dimension of R3 is going to be 3. Let me just note that here. The dimension of R3 is going to be 3 because we have 3 vectors in the basis set. And so, again, we'll prove this later on. So suppose a finite vector space has dimension n, let's say, then any set of n linearly independent vectors will be a basis for V. So again, if you have a bunch of, say, n linearly independent vectors, and for a vector space has dimension n, then that set of linearly independent vectors will be a basis. And you can go further than that. You can say, suppose a finite dimensional vector space V has dimension n. Then you can say several things. Any set with less than n vectors cannot be a basis for V. In particular, such a set will not span V. And B, any set of vectors and let me say it this way, any set with more than n vectors cannot be a basis for V. In fact, in particular, such a set will be linearly dependent. So again, if you have dimension n, you need at least n vectors to span the set. If you have less than that, it won't even span the set. If you have more than n vectors, those vectors will be linearly dependent. And let me mention a couple more theorems, and we'll prove these later on. Suppose U1 and U2 are subspaces of a finite dimensional vector space V, then the dimension of U1 plus U2. Remember from previous lectures, this means we're adding the vectors. Remember, that's not union. We're adding the vectors in each of these subspaces together. The dimension of this addition will be equal to the dimension of U1 plus the dimension of U2 minus the dimension of that intersection. The dimension of this sum of those two spaces, those two subspaces, that is equal to this. My equal signs are kind of messy. Let me fix that. And let me do one more here. And so suppose V is a finite dimensional subspace and V1, excuse me, U1, U2, UN, let's say, or let me call this K this time, UK are subspaces of V such that you can get all of V by adding those spaces together. And so let's say this is true, and the dimension of V is equal to the dimension of U1 plus the dimension of U2 plus the dimension of UK. So you have these two K's, you get the whole vector space by adding these spaces together. And the dimension of these individual ones come out to be the same as V. Then this means V is a direct product of these. Like this. And once again, we'll prove these a little bit later. But the idea is if V is equal to this, and yet the dimensions of these, or the sum of these is equal to V, that this statement right here sort of implies that there's no overlap between these here. Because if say one of these was a subset of the other, or if the intersection of any of these two subspaces was not the zero vector, then the dimensions on the right-hand side could possibly add up to more than the dimension of V. So these two together kind of indicate you have all of V here, yet you don't have anything extra. And if you have those two things, then V will be the direct product of those subspaces.